Hi, I am Kush Gaur and my roll number is 1910110213. So this is regarding maths and SEM assessment. We will be solving question 6. So here we go. So the question says consider the ODE y double dash plus 16y is equal to 4 delta t minus 3 pi. And the initial conditions are y0 is equal to 0 and y del 0 is equal to 0. So the first part says what kind of a real life phenomena is captured by the delta function if this ODE represents a mass spring system. So first I will talk about the direct delta function. So del x minus a. So it has value 0 when except at point A, and it is infinity when x is equal to a. So basically it reaches infinity when x is equal to a. So this is the basic definition of direct delta function that we have. So now if we see this in real life situation, now this direct delta function gives us an impulse. It is just like an impulse. So in real life, the real life phenomena which it exhibits is like a short impulse. Okay, so I will talk about some of its properties. So the properties which this function has is integral delta x minus a dx on the interval b to c is 1. First property. And the second property is integral b to c on the limits gx into delta x minus a is equal to g of a. So these are some properties. So now we will talk about the equation, which is y double dash plus 16y equal to 4 del t minus 3 pi. So this represents a mass spring system with external force as the direct delta function. So the phenomena which it exhibits, so the non-homogeneous ODE. So it exhibits a hammer response on the mass spring system. It is for a very short time, like quickly, like an impulse. So the real life phenomena which it exhibits is a hammer response on the mass spring system. Okay, so this was the phenomena and this is the answer of the first part. So now we'll be solving the second part. So the second part says, without solving and just using our intuition, sketch the graph of the solution. So now we have to sketch the graph of the solution by not solving it. So the equation is y double dash plus 16y 4 delta t minus 3 pi. So let me compare it with the general differential equation of a mass spring system. So general equation is y double dash plus cy dash is plus ky is equal to RT. Here C is the damping constant, and as you can see, the damping constant here is 0 because y dash is not here in the ODE. So C is equal to 0 and K is 16. So as the damping constant is 0, so this is an undamped condition. So now as we see, if time is less than 3 pi, then this non-homogeneous ODE is always 0 for time less than 3 pi. Also, as you know that a damping constant is 0, so the motion which it will exhibit is an SHM motion. It's very important. So the motion it exhibits is SHM motion because the damping constant is 0. So as you can see, the solution of this homogeneous equation would be a superposition of a cos function and a sine function, because it exhibits SHM motion. So YH will be A cos omega t plus B sine omega t. So it will be superposition of of a cos function and a sine function. So the initial conditions that we have are y0 is equal to 0 and y delta 0 is also 0. Okay, so when time is greater than 3 pi, so then the solution will be either of the two, either the cos function or the sine function. So there will be two graphs, one of the cos function t y, it will be time is greater than 3 pi. So first we will make the sine function graph, or it will be either of the two, or either the sine function or the cos function. Sorry, it's 3 pi. So I just made one cycle, so either it will be a sine function or a cos function. Okay, so now we will solve the C part. So the C part says solve the ODE and then sketch the graph of the solution, and then also we have to compare the two graphs. Okay. So the equation as we have is y double dash plus 16y is equal to 4 delta t minus 3 pi. Okay, so we will solve this differential equation using Laplacian. So taking Laplacian both sides, 16y is equal to Laplace 4 delta t minus 3 pi. Okay, so now we will use the linear property and we can distribute this. We will use the linear property of Laplacian and we will distribute this. So it will be like L y double dash plus 16 Laplacian y is equal to 4 Laplacian delta t minus 3 pi. Cool. So now we will use some identities. So the first identity which we are going to use, we will not use this, we will use this, like it's like L y dash is equal to S into Laplacian of y minus y of 0, and here S is a complex variable. The second identity is L y double dash is equal to S into Laplacian of y dash minus y dash 0. So we will put 1 into, so it will be L y double dash is equal to S square Laplacian of y minus S y 0 minus y dash 0. Now as we have the initial conditions y0 is equal to 0 and y dash 0 is equal to 0, so both of them will get cancelled. So we will just be left with Laplacian of y double dash is equal to S square Laplacian of y. It's really important, we will be going to use this. So we will use this in this. So let me turn the page. So now it will be S square Laplacian of y plus 16 Laplacian y is equal to 4L delta t minus 3 pi. Will be 4 Laplacian delta t minus 3 pi. Okay, so now we will take out a Laplacian of y common, so it will be S square plus 16 is equal to 4 Laplacian delta t minus 3 pi. Now we will focus on this term. So as I have told you earlier about this identity of the delta function, this one, second one, so we will going to use this. So we will use this. So the identity was integration on the limits b to c gt into delta t minus a dt is equal to ga. And by definition of the Laplacian function, we know Laplace of any function f is equal to integral 0 to infinity e to the power minus st into ft into dt, where s is a complex variable and t is always greater than 0. Okay, so now we will use this and we will do the Laplacian of delta t minus 3 pi is equal to integral 0 to infinity e to the power minus st into delta t minus 3 pi into dt. So now we will solve this using this. So it will be e to the power minus 3 pi t, because here a is 3 pi and gt is minus st. So it will be e to the power minus 3 pi t. So now Laplacian of delta t minus 3 pi is e to the power minus 3 pi t. So now we will use this over here. So now we will put this in this. So it will be Laplacian of y s square plus 16 is 4 into e to the power minus 3 pi t. So we will just take it in the denominator is equal to 4 into e to the power minus 3 pi t by s square plus 4 square, to be more precise. So the y will be Laplacian inverse e to the power minus 3 pi t into 4 by s square plus 4 square. So this is the answer. So now we will simplify it more for the graph purpose. So now we can solve this using time shift theorem. So the time shift theorem states that time shift theorem, Laplacian of any function t minus a into Heaviside or unit step function u t minus a is equal to e to the power minus at into f of s, and here f of s is the Laplacian of the function f. So now we're going to use this. So now we will just use this. So f t minus a into u, which is the unit step function of the Heaviside function, u t minus a is equal to Laplacian inverse e to the power minus at into f s. Now as we know, this is 4 by s square plus 4 square is equal to w by s square plus w square. Here w is 4. So we will find the Laplacian of sine omega t, which is omega by s square plus omega square. So it will be L sine Laplacian of sine omega t will be 4 by s square plus omega square, 4 square, because we know omega is and w is 4. So this is equal to this. So now we will put this here. Oh sorry, it's actually 4 because omega is 4. So L sine 4t is 4 by s square plus 4 square. So we will put sine 4t over here. So it will become y is equal to Laplacian inverse e to the power minus 3 pi t into Laplace of sine 4t. Okay, so now we will use this property and we will simplify this we will simplify this in the form of this. So we can see a here is 3 minus 3 pi and the function fs is Laplacian of sine 4t. So we will use this and we will write y is equal to sine 4 t minus 3 pi into u t minus a, and a is 3 pi, so t minus 3 pi. So this is the solution or the motion that this mass spring system exhibits. Okay, so now we will simplify it a bit to make the, so let's simplify it. Y is equal to sine 4t minus 12 pi into unit side function or heavy side function t minus 3 pi. So it will be y is equal to u t minus 3 pi into sine 4t minus 12 pi, and we will just use its property, so it will get finished. So y is equal to u t minus 3 pi into sine 4t. So now if we graph this, here is time, here is y. So let's graph this. So the time is 3 pi. So after this the function will begin, because below this the time basically when the time is less than 0, it will be always 0. So it's always 0. After 3 pi it will be a graph of sine 4t. It will be a little bit squeezed because its frequency is 4 times. So it will be like this, and it will go up till infinity. So before 3 pi the value is 0 of y. Now it will follow the sine 4t graph, and this goes on infinitely due to undamped conditions. So now we have to compare this graph and the one which we have made using our intuition. So these are the graphs which we made using our intuition. So I think that's the same. So I earlier also I said that we will use either this or this. So we have this and the graph which is there. So these are the exact same. Almost this is the function of sine omega t, but we didn't know the value of omega. Now we know the value of omega, so it's sine 4t. So it's approximately the same, as you can see. Also I would like to define the u t minus 3 pi. So first I will define unit side function u t minus a. So it is always 0 when t is less than a, and is 1 when t is greater than a. So I think I have solved everything. Let's recapitulate. So the phenomena is the Hammer response on the mass spring system for a very short period of time, and the graph which I made was either this or this, and actually it's this, and the solution is this sine 4t minus 3 pi into u t minus 3 pi, which we again simplified into this. Then this is the graph. So these are the answers. So this is it. Thank you.